Now in this lecture I'll answer on two questions. In the first question we find out the area of this green shape that is inside square TSQP, and in the second question we find out the area of this green shape that is inside square ABCD. So we start with the first question. In the drawing we have two squares. We have the big square TSQP and the small square ABCP. In addition, we know that the area of this triangle AMP is equal to 9 square units in its size, and the area of this quarter circle, the area of this quadrilateral MBCP is equal to 27 square units in its size. Again, our task is to find out the area of this green shape. So first of all, we know that ABCP, quadrilateral ABCP is a square, and the area of this square ABCP in total it is equal to 9 plus 27, that is 36 square units in its size. So I write it down. The area of square ABCP is equal to 36 square units in its size. And again, the area of the small square ABCP is equal to 36 square units in its size. You also know that the area of any square equals to the length of one side squared. And therefore, the area of this square ABCP must be equal to the length of side AP squared. So, from one side, the area of square ABCP equals to 36 square units in its size, but from the other side, the area of square ABCP equals to the length of side AP squared. And from this equation, AP squared equals to the area of square ABCP equals to 36. We derive that AP squared equals to 36. Here we take a root out of this equation, and finally we get that the length of side AP of square ABCP is equal to the square root of 36, that is 9. So side AP of square ABCP is equal to 9 units in its length. The length of side AP is the square root of 36, that is 6. So AP equals to 6 units in its length. This is side AP, that is equal to 6 units in its length. We know that ABCP is a square, and we know that all the angles inside the square are right angles. Therefore, this is a right angle. It is 1 out of 4 angles in square ABCP, and therefore it is equal to 90 degrees in its size. And therefore, this is the right triangle PAM. In the right triangle PAM, side AB equals to 6 units in its length, and we know that the area of this right triangle AMP equals to 9 square units. So I write it down. The area of the right triangle AMP is equal to 9 square units in its size from one side, but from the other side, you know that the area of any triangle equals to the base of the triangle, that is AM, times the height AP over 2. From one side, the area of the right triangle AMP equals to 9 square units in its size, but from the other side, the area of the right triangle AMP equals to the base AM times the height AP over 2. Because again, from one side, the area of the right triangle AMP equals to 9 square units inside, but from the other side, the area of triangle AMP equals to the base of the triangle, that is AM, times the height AP over 2. So it is AM times AP. AP is 6 over 2. And from this equation, we will derive that AM times AP over 2 equals to 9. So AM times 6 over 2 equals to 9. 6 over 2 is 3, so in total this expression equals to 3 times AM is equals to 9. So 3 times AM equals to 9. Here we divide this equation by 3. And we get that AM equals to 9 over 3 is 3. So side AM, or the right triangle AMP equals to 3 units in its length. This is side AM, is equals to 3 units in its length. In the next step, we will implement the Pythagoras theorem on the right triangle, triangle AMP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So it will be the right triangle AMP in an equation. We will implement to this right triangle the Pythagoras theorem. Here by PT is the abbreviation for Pythagoras theorem. Actually, this is the right triangle AMP that is covered from the original domain. In this right triangle AMP, according to the Pythagoras theorem, MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. So let it know. MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so leave it as it is. It is MP squared is equal to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus AP squared. AP is 6, therefore AP squared is 6 squared, that is 36. So in total, MP squared equals to 9 plus 36, that is 45. MP squared equals to 45. Here we substitute 45 by 9 times 5. We get that MP squared equals to 9 times 5. Here we take a root out of this equation and finally get that MP, the length of the hypotenuse MP, is equals to the square root of 9, that is 3. So inside the brackets we left only with, inside the root we left only with 5. So it is 3 times root of 5 units in its length. This is the hypotenuse MP, that is equals to 3 times root of 5 units in its length. We know that all the angles inside the square are right angles, so in the big square TSQP, this angle equals to 90 degrees. It is 1 out of 4 angles of square TSPQ. Therefore, it is equal to 90 degrees in its size. In the next step, we'll focus on the small right triangle TBM and on the right big triangle AMP. Those two angles are defined as vertex angles. We know that vertex angles are equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. So in the small right triangle MTB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. According to the sum rule, the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right triangles are similar to each other according to angle similarity rule. I will explain anyway why those two right triangles are similar to each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So in total, we found out that all the angles of the big right triangle AMP are corresponding equal to all the angles of this small right triangle TMB. Therefore, those two right triangles are similar to each other according to angle similarity rule. So write it down. We actually found out that the big right triangle PAM is similar. This is the sign of similar to the small right triangle TMB. This small right triangle according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle AMP over side TB of the small right triangle TBM equals to side AM of the big right triangle AMP over side TM of the small right triangle TMB, and it is also equals to side MP of the big right triangle AMP over side MB of the small right triangle TMB. Okay, again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle PAM or side TB of the small right triangle TMB equals to side AM of the big right triangle PAM or side TM of the small right triangle TMB, and it is also equal to side MP of the big right triangle PAM or side MB of the small right triangle TMB. Before we continue, we'll find out the length of this side MB. MB equals to AB minus AM. Okay, again, the missing side MB equals to AB minus AM. So MB equals to AB. AB is 6 because of the fact that all the sides of this square ABCD are equal to each other. One side AP is 6 and the other side AB must be also equal to 6 minus AM. AM is 3. So in total MB equals to 6 minus 3, this is 3. So MB equals to 3 units in its length. This is side MB is equals to 3 units in its length. And found out that from the fact that those two articles are similar to each other, we derive that the following relationship exists between their sides, that AP over TB equals to AM over TM equals to MP over MB. AP is 6 over TB. TB is the missing side, so we leave this it is. And it is equal to AM. AM is 3 over TM. TM is the missing side, so we leave this it is. And it is equal to MP. MP is 3 times square root of 5 over MB. MB is 3. So in total, we actually found out that 6 over TB equals to 3 over TM equals to 3 times square root of 5 over 3. So we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we left only with square root of 5. So in total, we actually found out that 6 over TB equals to 3 over TM equals to the square root of 5. Those two expressions are equal to each other, so we get the first equation from those two expressions that are equal to each other. This is to say 3 over Tm equals to the square root of 5. Here we will multiply this equation by Tm and then we will divide it by square root of 5 simultaneously, and we get that Tm will be equal to 3 over square root of 5 units in its length. So okay, this is the missing side Tm is equal to 3 over square root of 5 units in its length. Those two expressions are equal to each other, so we get the second equation from those two expressions that are equal to each other. We get that 6 over TB equals to the square root of 5. Here we multiply this equation by TB and then we divide it by square root of 5, and we get that TB equals to 6 over square root of 5 units in its length. Okay, this is side CB. This equals to 6 over square root of 5 units in its length. What is the length of side TP? TP in total equals to TM plus MP. So TP equals to TM plus MP. And again, TP equals to TM plus MP. for TP in total equals to TM. TM is 3 over square root of 5 plus MP. MP is 3 times square root of 5. So in total, we should find out that the length of side TP of square TSQP, in total it is equal to 3 over square root of 5 plus 3 times square root of 5. So TP equals to 3 over square root of 5, and here we multiply 3 times square root of 5 by square root of 5, and then we divide it by square root of 5 in order to overcome factor with this number, and we get that 3 times square root of 5 times square root of 5 is square root of 5 times square root of 5 is 5, and 5 times 3 is 15 over square root of 5. So in total we found out that TP equals to 3 plus 15 over square root of 5. So TP equals to 3 plus 15 is 18 over square root of 5. So TP in total equals to 18 over square root of 5 units in its length. So this is side TP. This equals to 18 over square root of 5 units in its length. TP equals to 18 over square root of 5 units in its length. Our task is to find out the area of this green shape. So, what is the area of the green shape? The area of the green shape, in total it will be equal to the area of the big square TSQP minus the area of this quadrilateral MBCP It is given as the question that the area of quadrilateral MBCP is 27 square inches in size, minus the area of this small rectangle TBM. Then again, the area of this green shape equals to the area of the big square TSQP minus the area of this quadrilateral TSCP, that is equals to 27 square units in size, minus the area of this small rectangle TBM. And again, the area of the green shape in total equals to the area of the big square TSQP minus the area of quadrilateral MBCP. It is given as the question that it is equals to 27 square units in size minus the area of the small rectangle TBM. What is the area of the big square TSQP? The area of the big square TSQP will be equal to one side squared, the length of side TP squared, TP squared, minus the area of this quadrilateral MBCP. It is given as a question that quadrilateral MBCP equals to 27 square units in its size, minus the area of this small rectangle TBM. The area of the small rectangle TBM will be equal to the base of this rectangle TBM, that is TB, times the height, that is TM, divided by 2. And again, the area of this small rectangle TBM equals to the base TB times the height this is actually Tm over 2. So there of the big square TSQP equals to TP square. We've already found out that TP equals to 18 over square root of 5, and the whole TP squared will be equal to 18 over square root of 5 squared minus 27 minus thereof the small right area TBM is equals to TB times Tm over 2. TB is 6 over square root of 5 times Tm. Tm is 3 over square root of 5 divided by 2. And 18 over square root of 5 squared equals to 18 squared, that is 324, over square root of 5 squared, that is 5, minus 27, minus, here we have 6 times 3 is 18, over square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total this expression equals to minus 18 over 10. So the area of the green shape will be equal to 324 over 5 is 64.8 minus 27 minus 18 over 10 is minus 1.8. 64.8 minus 1.8 is 63, and 63 minus 27 is 36. So in total we found out that the area that we are looking for in this question, that is the area of this green shape, it is equal to 36 coordinates in its size. So I write it down, and we found out that the area of the green shape is equal to 36 square units in size. So we finish with the first question. In the next step, I'll present you the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this green shape that is inside square ABCD. So we know that one side of square ABCD equals to 10 units in its length, and inside this square ABCD we have this quarter circle. We know that the center of this quarter circle is located here at point A. In addition, inside this square ABCD we have this semicircle, and the diameter of the semicircle, the diameter of this semicircle is BC, that is equals to 10 units in its length. If the diameter of this semicircle is 10, it means that the radius must be equal to 10 over 2, that is 5. We define the center of this semicircle, this point is point O. So the radius OB equals to 5, that is the radius of the semicircle. The radius OC also equals to 5. And we know that point A is the center of the quarter circle, point B is the point of the quarter circle itself, therefore AB is the radius of the quarter circle, that is 10. Likewise, AD is also the radius of this quarter circle, is equal to 10 units in its length. In the next step, we will join points, we'll define the intersection point between this quarter circle and this semicircle. This point is point M. In the next step, we'll join points A and M together by a straight line. Point A is the center of the quarter circle, point M is the point on the quarter circle itself, therefore AM is the radius of the quarter circle. This equals to 10 units in its length. The next step, we'll join points O and M together by a straight line. Point O is the center of this semicircle, point M is a point on the semicircle itself, therefore OM is the radius of this semicircle. This is equals to 5 units in its length. What is the definition of line segment AM? Line segment AM is tangent to the semicircle at point M. Again, line segment AM is tangent to this semicircle at point M. So, in the drawing, we have the radius OM, this is equals to 5, the radius OM of this semicircle, this is equals to 5, is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees according to rule 1. This is angle ABC. That is the right angle because of the fact that it is 1 out of 4 angles of square ABCD, and you know that all the angles inside the square are right angles. So angle ABC equals to 90 degrees in its size. In the next step, we'll join points A and O together by a straight line. By joining points A and O together, those two right angles. This is the right angle AOM and this is the right angle AOB. So, in the next step, we'll prove those two right angles can go into each other according to side rule. So, write it down. We prove that the right angle AOM, this is the right angle AOM, congruent to this right angle AOB or ABO according to side rule. So, why those two right angles can go into each other? First of all, side OB of the right angle AOB equals to side OM of the right angle AOM. They're both the area of the semicircle, that equals to 5, and therefore they are equal to each other. So, OB equals to OM equals to 5. Side OB of the right angle ABO equals to side OM of the right angle AOM. They're both the area of the semicircle that is equal to 5, and therefore they are equal to each other. In addition, we have side AB of the right angle ABO is equal to side AM of the right angle AOM. They are both the area of the quarter circle that is equal to 10, and therefore they are equal to each other. So side AB of the right angle ABO equals to side AM of the right angle AOM. They are both the area of the quarter circle that is equal to 10, and therefore they are equal to each other. And again, AB equals to AM equals to 10. And finally, this is side AO, that is a common side that belongs to both triangles, so we can write down that AO equals to itself is a common side that belongs to both triangles. So if we found out that all the three sides of this right triangle ABO corresponding equal to all the three sides of this right triangle AOM, and therefore those two right triangles can go into each other according to side rule. So write it down. If we found out that the big right triangle ABO congruent, this is the sign of congruent to the big right triangle AOM according to side rule. And for the fact that those two right triangles can go into each other, we will derive that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, we also, for the fact that those two angles can go into each other, we will derive that those two angles must be also equal to each other according to the same rule that corresponding angles in congruent triangles are equal to each other. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. In the next step, we will focus on the right triangle ABO. This is right triangle ABO, and I'll copy this right triangle ABO in a new page and we'll implement the Pythagoras theorem on this right triangle ABO. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the version for Pythagoras theorem. Side AB equals to 10 units in its length, side BO equals to 5 units in its length, and the hypotenuse AO is the missing side. So this is the right triangle ABO that according to the original drawing. This right triangle ABO, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. So I'll write it down. AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, so it is AO squared equals to AB squared. AB is 10, therefore AB squared is 10 squared, that is 100, plus BO squared. BO is 5, therefore BO squared is 5 squared, that is 25. So in total we should know that AO squared equals to 100 plus 25, that is 125. AO squared equals to 125. Here we substitute 125 by 25 times 5 and we get that AO squared equals to 25 times 5. Here we take a root out of this equation and finally we get that the area for the hypotenuse AO it is equal to the square root of 25, that is 5. So inside the root we left only 5. So in total, AO equals to 5 times square root of 5 units in its name. This is side AO. Is equals to 5 times square root of 5 units in its length. We continue to focus on the right triangle ABO. The right triangle ABO sinus alpha equals to BO over AO. Again, in the right triangle ABO, sinus alpha equals to BO over AO. So sinus alpha equals to BO. BO is 5 over AO. AO is 5 times square root of 5. So in total, we shall know that sinus alpha equals to 5 over 5 over 5 times square root of 5. We have 5 in the denominator, 5 in the denominator, so 5 will get cancelled. We left only with 1 over square root of 5. So in total, we shall know that sinus alpha equals to 1 over square root of 5. Our task is to find out the value of angle alpha itself. In order to find out the value of angle alpha, we'll operate the opposite function of sine, that is arc sine, on the result. This will give us the value of alpha itself. So we'll operate the function arc sine. This is the opposite function of sine on the result, that is 1 over square root of 5. This will give us the value of alpha itself. And you can find it when checking, by calculating in any calculator, that arc sine of 1 over square root of 5, it is actually equals to 26.565 degrees. So in total, we know that angle alpha equals to 26.565, and therefore 2 alpha will be equal to 2 times 26.565. That is actually 53.13 degrees. So the big angle BAM, it is alpha plus alpha, that is 2 alpha. Now if you found out that the big angle BAM, this was to 2 alpha, is equal to 53.13 degrees. We know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right triangle ABO must be equal to 180 degrees. So which angles we have in the right triangle ABO? We have alpha plus beta plus 90 degrees. In total, they must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So here alpha plus beta plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation, and we get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation, and we get beta equals to 90 degrees minus alpha. Beta equals to 90 degrees minus alpha, and therefore beta equals to 90 degrees minus alpha, and alpha is 26.565, and 90 degrees minus 26.565 is equal to 63 0.435 degrees. So angle beta equals to 63.435 degrees, and therefore 2 beta equals to 2 times 63.345 degrees. This is actually 126.87 degrees. This is the big angle beta plus beta, this is 2 beta, and it is equal to 126.87 degrees. Okay, so our task is to find out the area of this green shape. So first of all, we join points M and B together by a straight line. When joining points M and B, we divided the green shape into 2 parts. The first part is the upper segment MB, and the second part is the lower segment MB. So we define the upper segment, this upper segment as segment MLB. We define the upper segment, this upper segment is BUM. The upper segment is segment BUM, and we define the lower segment as segment BLM. And we'll find out separately the area of the upper segment BUM and the area of the lower segment BLM. We let the 2 areas of those 2 segments with each other, and this will be the area of this green shape. So in the next step, I'll copy sector A and B in a new page, and we analyze this sector A and B, or ABM. This is again 2 alpha, is actually equals to 53.13 degrees. AB equals to AM equals to 10. It's actually those 2 sides are the radii of the quarter circle. It is equals to 10 units in its length. This is sector ABM. The round sign above ABM is a sign for a sector. So first of all, what is a definition of a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between the 2 radii, the arc PM. It again. the green shape A or B is a sector. You can see that a sector is a portion of a circle enclosed by two radii, AU equals to R, BU equals to R, above the radii of the circle, and RKB between the two radii. And the angle between the two radii is theta. The two radii are also defined as the legs of the sector, and the area of this sector A or B equals to the area of the circle that contains the sector, that is pi r square, r is the radius of the circle, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again, a sector is a portion of a circle enclosed by two radii and the arc between them, RKB, and the area of the sector is equal to pi r square, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So use the new formula in order to find out the area of this sector, sector ABM. According to the formula that I presented to you, the area of this sector ABM will be equal to the area of the circle that contains the sector, that is pi r square. R is the radius of the quarter circle, that is equal to 10, times the angle between the legs of the sector, that is 53.13 degrees, over 360 degrees. R is the radius of the quarter circle, that is equal to 10, therefore r squared is 10 squared, that is 100, so pi r squared is 100 pi, times 53.13 degrees over 360 degrees. The value of this expression, that is to say 100 pi times 53.13 degrees over 360 degrees, in total this expression equals to 46.3646 square units in its size. 46.3646 square units in its size. So the area of this sector AMB or ABM equals to 46.3646 square units in its size. Our task is to find out the area of the lower segment BLM. This is the lower segment BLM. Our task is to find out the area of this lower segment BLM. So what is the area of the lower segment BLM? This is the lower segment BLM. What is the area of the lower segment BLM? The green shape is the lower segment BLM. So what is the area of this lower segment BLM? From the drawing it is very easy to see that the area of this green lower segment BLM is equal to the area of sector AMB This is sector AMB or ABM minus the area of triangle ABM. Minus the area of this triangle ABM. repeat again. It is very easy to see from the drawing that the area of this lower segment BLM equals to the area of sector ABM minus the area of triangle ABM. If you take from the sector ABM, triangle ABM, we're left only with segment BLM. But again, the area of segment BLM equals to the area of sector AMB minus the area of triangle ABM. We have already found out that the area of this sector ABM equals to 46.3646 square units in its size. Minus the area of this triangle times ABM. AB equals to 10, AM also equals to 10, and the angle between side AB and side AM is 53.15 degrees. So in the next step I will present to you a new formula that will help us to find out the area of this triangle ABM. This is triangle ABM that could be any triangle. Side AB of triangle ABM equals to A units in its length, side AC equals to B units in its length, and the angle between the sides AB and AC is angle theta. So the area of this triangle ABM that could be any triangle equals to A times B, that is the multiplication of the two sides by each other, times the angle between the two sides, that is times sinus the angle between the two sides, that is theta over 2. Again, the area of this triangle ABM equals to A times B times sinus theta over 2. So we use the new formula in order to find out the area of this triangle ABM. According to the new formula that I presented to you, the area of this triangle ABM will be equal to AB times AM, that is the multiplication of the two sides by each other, times sinus the angle between the two sides, that is 53.13 degrees over 2. And again, the area of this triangle ABM equals to AB times AM times sinus the angle between the two sides, that is 53.13 degrees over 2. So the area of triangle ABM will be equal to AB is 10 times AM is also 10, so 10 times 10 is 100. Sinus 53.13 is 0.8 over 2. 100 over 2 is 50, and 50 times 0.8 is 40. So in total, we should found out that the area of this triangle ABM is equal to 40 square units in its size. And the area of this lower segment BLM equals to the area of sector ABM, that is 46.3646 square units in its size, minus the area of this triangle ABM, that is 40 square units. 46.3646 minus 40 is 6.3646. So in total, we should know that the area of the lower segment BLM is equal to 6.3646 square units in its size. In the next step, we'll find out the area of the upper segment BUM. This is the upper segment BUM. We'll find out the area of this upper segment BUM. So, in order to find out the area of this segment BUM, I'll copy sector OBM in a new page and we'll analyze this sector OBM. This is sector OBM. Two beta, the angle between the legs of sector OBM is 2 beta. This is actually 136.87 degrees. OB equals to 5, this is the radius of the semicircle. OM also equals to 5, this is the radius of the semicircle. So actually, this is sector OBM, that I come from the original drawing. The area of sector OBM, according to the formula that I presented to you a couple of minutes ago, will be equal to pi r squared. That is the area of the circle that contains the sector, that is actually the semicircle. Pi r squared is the area of the circle, of course, times the angle between the legs of the circle, that is actually 126.87 degrees over 360 degrees. R is the radius of the semicircle, that is 5. Therefore, r squared is 5 squared, that is 25. So pi r squared is 25 pi times 126.87 over 360 degrees. In total, the value of this expression, 25 pi times 126.87 degrees over 360 degrees. In total, this expression equals to 27.678 square units in its size. This is equal to 27.678 square units in its size. So in total, we found out that the area of this sector OBM is equal to 27.678 square units in its size. Our task is to find out the area of the upper segment BUM. This is the upper segment BUM. So what is the area of the upper segment BUM? This is the upper segment BUM. This is the same upper segment here, BUM. So we have to find out the area of this upper segment BUM. So what is the area of the upper segment BUM? From the drawing, it is very easy to see that the area of upper segment BUM will be equal to the area of sector OBM. This is the area of this sector. Angle between the legs of the circle is 126.87 degrees. BU equals to 5, OB also equals to 5. We already found out that the area of the sector BUM equals to 27.678 square units in its size. So the area of segment BUM equals to the area of sector BOM minus the area of triangle BOM. Minus the area of this triangle BOM. It's very easy to see from the drawing that if you subtract the area of triangle BOM from the area of sector BOM, so you will remove the triangle and only segment BOM will be left. And therefore, the area of segment BOM equals to the area of sector BOM minus the area of triangle BOM. We already found out that the area of sector BOM equals to 27.678 square meters in size minus the area of triangle BOM. According to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM will be equal to BO times OM times sinus 126.87 degrees over 2. Sinus 126.87 degrees over 2. BO is 5, OM is also 5, so 5 times 5 is 25. Sinus 126.67 is 0.8. And we have to divide it by 2. 25 over 2 is 12.5, and 12.5 times 0.8 is 10. So in total we should know that the area of this triangle BOM is equal to 10 square meters in its size. And the area of this segment BOM equals to the area of sector BOM, that is 27.678, minus the area of this triangle BOM, that is 10. 27.678 minus 10 is 17.678 square meters in its size. So in total we should know that the area of this segment BOM equals to 17.678 square meters in its size. Our task is to find out the area of this screen shape. So the area of this screen shape will be equal to the area of the upper segment BOM, that we should find out just right now, that it is equal to 17.678 square meters in size, minus the area of the lower segment BLM. We already found out that the area of the lower segment BLM equals to 6.346 square meters in size. So the area of this green shape will be equal to the area of the upper segment BUM, that is 17.678, plus the area of the lower segment BLM, that is equal to 6.3646 square meters in size. So the area of the green shape in total is equal to the area of the upper segment BUM, that is equals to 17.678 square meters in size, plus the area of the lower segment BLM, that is equal to 6.346 square meters in its size. So again, we should know that the area of the green shape equals to the area of the upper segment BUM, that is equal to 17.678 square meters in size, plus the area of the lower segment BLM is equal to 6.346 square meters in size. And 17.678 plus 6.346 is equal to 24.0426 square meters in its size. So the area of the green shape is equal to 24.0426 square meters in its size. And again, we should know that the area of this green shape, that is the area that we are looking for in this question, is equal to 24.0426 square meters in its size. So we finish with the second question. In the next step of summarize the lecture, we'll start with the first question, of course. first question, our task is to find out the area of this green shape that is inside square TSQP. So in the domain we have the big square TSQP. This is the small square ABCP. And we know that this is quadrilateral MBCP. This is equals to 27 square units in size. This is triangle MAP. This is equal to 9 square units in size. Again, our test is to find out the area of this ring shape. So first of all, we know that the area of the small square ABCP equals to 27 plus 9, that is 36 square units in size. And again, the area of the small square ABCP is equal to 36 square units in size from one side, but from the other side, the area of this small square ABCP equals to the area of any square equals to the length of one side squared, and therefore it will be equal to the length of side AP squared. So from the other side, the area of the small square ABCP equals to AP squared. From this equation, we will derive that AP squared equals to 36. Here we take a root out of this equation and we get that AP equals to the square root of 36, that is 6. This is side AP, this is equals to 6 units in its length. So we know that the area of this, first of all, we know that quadrilateral ABCP is a square, and therefore all the angles inside the square are right angles, and therefore this is 1 out of 4 angles of square ABCP, and therefore it must be equal to 90 degrees in its side. So we know that the area of this right triangle AMP is equal to 9 square units. So from one side, the area of the right triangle AMP equals to 9 square units in its size, but from the other side, the area of this right triangle AMP equals to the base of the triangle that is AM times the height AP over 2. So from the other side, the area of the right triangle AMP equals to the base AM times the height AP over 2. AP is 6, so we solve AP by 6, and we get that AM times 6 over 2 equals to 9. From this equation, we derive that AM times AP over 2 equals to 9. AP is 6, so AM times 6 over 2 equals to 9. 6 over 2 is 3, so in total this expression equals to 3 AM, so 3 AM equals to 9. Here we divide this equation by 3 and found out that AM equals to 9 over 3, that is 3. This is side AM, this equals to 3 units in its length. Actually, we know that all the sides of square ABCP are equal to each other. Its side equals to 6, and therefore AB also equals to 6. AB equals to 6, so AB minus AM equals to MB. And MB equals to AB minus AM. So MB equals to AB, that is 6, minus AM, that is 3. 6 minus 3 is 3, so MB equals to 3 units in its length. In the next step, I copied the right triangle AMP in an equation implemented the Pythagoras theorem on this right triangle AMP. This is the right triangle AMP that I copied from the original domain, and this right triangle AMP according to the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the square for the perpendiculars. So in the right triangle AMP, MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. Again, MP squared, that is the square of the hypotenuse, equals to AM squared plus AP squared. MP is the missing side, so leave it as it is, so it is MP squared equals to AM squared. AM is 3, therefore AM squared is 3 squared, that is 9, plus MP squared. MP is 6, therefore MP squared is 6 squared, that is 36. 9 plus 36 is 45. So in total, we should find out that MP squared equals to 45. Here we substitute 45 by 9 times 5, and found out okay, that MP squared equals to 9 times 5. Here we took a root out of this equation and finally found out that MP equals to the square root of 9, that is 3, so inside the root we left only with 5. So MP, MP equals to 3 times square root of 5 units in its length. This is side MP, this is equals to 3 times square root of 5 units in its length. We know that all the angles inside the big square TSQP are right angles, and therefore this angle is a right angle. It is one out of four angles of the big square TSQP, and therefore it is equal to 90 degrees in its sides. So in the next step, we'll focus on those two right angles. We'll focus on the right angle to TBM, and on the right big triangle AMP. Those two angles are defined as vertex angles, so we know that vertex angles are equal to each other. So if we define this angle as alpha, then this angle must be also equal to alpha because they are equal to each other. So in the small right triangle TMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the big right triangle AMP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the symbol, that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the angles of the big right triangle AMP are corresponding equal to all the angles of the small right triangle TBM, and therefore those two right triangles are similar to each other according to angle similarity rule. And again, if you found out that triangle, the big triangle PAM is similar, this is the sign of similar, to the small right triangle TMB according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM over side TB of the small right triangle TBM equals to side AM of the big right triangle AMP over side TM of the small right triangle TBM, and it is also equal to side MP of the big right triangle AMP over side MB of the small right triangle TBM. But again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle PAM or side TB of the small right triangle TMB equals to side AM of the big right triangle PAM or side TM of the small right triangle TMB, and it is also equals to side MP of the big right triangle PAM or side MB of the small right triangle TMB. AP is 6 over TB. TB is the missing side of verticity, and it is equals to AM. AM is 3 over TM. TM is the missing side of verticity, and it is also equals to MP. MP is 3 over square root of 5 over MB. MB is 3. So into that, we should know that 6 over TB equals to 3 over TM equals to 3 over square root of 5 over 3. We have 3 in the numerator and 3 in the denominator, so 3 will get cancelled, and we left only with square root of 5. So in total, we should find out that 6 over TB equals to 3 over TM equals to the square root of 5. Those two sides are equal to each other, so we get the first equation from those two sides that are equal to each other. Actually, those two sides are equal to each other, so we get the first equation from those two sides that are equal to each other. That is to say, 3 over Tm equals to the square root of 5. 3 over Tm equals to the square root of 5. Here we multiply this equation by Tm, and then we divide it by square root of 5 simultaneously, and finally found out that Tm equals to 3 over square root of 5 units in its length. This is side Tm, this equals to 3 over square root of 5 units in its length. Likewise, those two sides are also equal to each other, so you get the second equation from those two sides that are equal to each other. According to the second equation, 6 over Tb equals to the square root of 5. 6 over Tb equals to the square root of 5. Here we multiply this equation by Tb, and then we divide it by square root of 5 simultaneously, and we found out that Tb equals to 6 over square root of 5 units in its length. This is side Tb. This equals to 6 over square root of 5 units in its length. what is the length of side TP? TP in total equals to TM plus MP. Again, TP equals to TM plus MP. And again, TP in total equals to TM plus MP. So TP equals to TM. TM is 3 over square root of 5 plus MP. MP is 3 over square root of 5. So in total, if you found out that TP equals to TM, that is 3 over square root of 5, plus MP, that is 3 times square root of 5. So in total, TP equals to 3 over square root of 5 plus 3 times square root of 5. So TP equals to 3 over square root of 5. Here we multiplied 3 times square root of 5 by square root of 5, and then we divided by square root of 5 in order to have a common factor with this number. And we should find out that TP equals to 3 over square root of 5, and square root of 5 times square root of 5 is 5, and 5 times 3 is 15. So in total, we have here 15 divided by square root of 5. So in total TP equals to 3 times 15 over square root of 5. 3 times 15 is 18 over square root of 5. So in total we should find out that TP equals to 18 over square root of 5 units in its length. This is side TP. This is equals to 18 over square root of 5 units in its length. Repeat again. Side TP equals to 18 over square root of 5 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing it is very easy to see that the area of the green shape in total equals to the area of the big square TSQP minus the area of this quadrilateral MBCP minus the area of this small right triangle TBM. And again, the area of the green shape in total equals to the area of the big square TSQP minus the area of quadrilateral MBCP. The area of quadrilateral MBCP is equal to 27 square units inside, according to what is given in the question, minus the area of this small right triangle TBM. Minus the area of the small right triangle TBM. So what is the area of the big square TSP? The area of the big square TSP. The area of any square equals to the length of one side squared. And therefore, the big square TSQP must be equal to the length of side TP squared. So it is TP squared minus the area of this quadrilateral MBCP, that is 27. So it is minus 27 minus the area of the small right triangle TBM. The area of this small right triangle TBM equals to the base TB times the ITM over 2. So the area of the small right triangle TBM equals to the base TB times the ITM over 2. We know that TP equals to 18 over square root of 5. Therefore, TP squared equals to 18 times square root of 5 squared minus 27. TB equals to 6 over square root of 5 times TM. TM equals to 3 over square root of 5. Repeat again. TB equals to 6 over square root of 5. TM equals to 3 over square root of 5 divided by 2. We have to divide it by 2. Here we have square of 18 over square root of 5 is square root of 18, that is 324 over square root of 5 squared is 5. So in total this expression equals to 324 over 5. This is actually the area of the big square TSQP minus 27, that is the area of quadrilateral MBCP. And here we have 6 times 3 is 18 over square root of 5 times square root of 5 is 5, and 5 times 2 is 10. So in total this expression equals to 18 minus 10, 18 over 10. 324 over 5 is 64.8 minus 27, and 18 minus 18 over 10 is minus 1.8. 64.8 minus 1.8 is 63 minus 27. 63 minus 27 is 36. So in total, if you want that the area that we are looking for this question, that is the area of this green shape, is equal to 36 square units in size. Repeat again, the area of this green shape equals to 36 square units in its size. So we finish with the first question. In the next step, I presented you the second question, and we solved the second question of this lecture. In the second question, our task is to find out the area of this green shape. So in the drawing, we have the big square ABCD. Inside, we know that one side of square ABCD equals to 10, therefore all the other sides must also equal to 10. Inside this square ABCD, we have this big quarter circle, and we have this semicircle. The diameter of the semicircle, this semicircle is BC. BC is 10. If the diameter BC is 10, then the radius must be equal to 10 over 2, that is 5. So the radius of B is 5, the radius of C is also 5. We know that the center of this quarter circle is at point A. So point A is the center of the quarter circle, point D is the point of the circle on the quarter circle itself, therefore AD is the radius of the quarter circle, that is 10. Likewise, AB is also the radius of the quarter circle, that is 10. So in the next step, we join points A and M together by a straight line. After we define the intersection point between the semicircle and the quarter circle, this point is point M. And we join points A and M together by a straight line. AM is also it's actually a tangent to the semicircle and point M. Point A is the center of the quarter circle, point M is the point of the quarter circle itself. Therefore, AM is the radius of the quarter circle, that is 10. In the next step, we join points O and M together by a straight line. Point O is, of course, the radius, the center of the semicircle. Point M is the point of the semicircle itself. Therefore, OM is the radius of the quarter circle, that is 5. Here we can implement rule 1 because we have the radius OM that is equal to 5. The radius OM is drawn to point M, that is the point of tendency of tangent AM with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius OM. If AM is perpendicular to OM, it means that this angle equals to 90 degrees according to rule 1. We know that all the angles inside square ABCD are right angles, and therefore this is a right angle. In the next step, we join points A and O together by a straight line. By joining points A and O, we get those two right angles. This is the right angle ABO, and this is the right angle AMO. In the next step, we prove that those two right angles can go into each other according to side rule. So why those two right angles can go into each other? First of all, OB equals to OM equals to 5. Those two sides are both equal to 5 and therefore they are equal to each other. In addition, AB equals to AM equals to 10. Those two sides are both equal to 10 and therefore they are equal to each other. And finally, AO is the common side that belongs to both angles. So we can write that AO equals to itself is the common side that belongs to both angles. So if you found out that all the three angles of the big right angle ABO are corresponding equal to all the three angles of the big right angle AOM. Therefore, those two right angles can go into each other according to side rule. And from the fact that those two right angles can go into each other, we will derive that those two angles must be also equal to each other, according to the rule that corresponding angles and congruent angles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other. So if we find the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. Likewise, from the fact that those two right angles can go into each other, we will derive that those two angles are equal to each other according to the same rule that corresponding angles and congruent angles are equal to each other. So if we find the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other according to the rule that I mentioned. So, in the next step, I copied the right angle ABO. In the new page, we implemented the Pythagoras theorem on this big right angle ABO in order to find out the hypotenuse AO. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right angle ABO that I copied from the original drawing. Side AB equals to 10, side BO equals to 5, and AO, the hypotenuse AO is the missing side. According to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AB squared plus BO squared. AO is the missing side, AO is the missing side, so we need to see this. So AO square equals to AB square. AB is 10, therefore B square is 10 squared, it is 100, plus BO square. BO is 5, therefore BO square is 5 squared, that is 25. So in total, AO square equals to 100 plus 25. 100 plus 25 is 125. So in total, we should find out that AO square equals to 125. Here we substituted 125 by 25 times 5, and found out that AO square equals to 25 times 5. Here we took out of this equation, and finally found out that AO equals to the square root of 25, that is 5. So inside the root we left only with 5. So in total, AO equals to 5 times square root of 5 units in Z. So actually, this is side AO, this equals to 5 times square root of 5 units in Z. In the next step, we continue to focus on the right triangle ABO. On the right triangle ABO, sinus alpha equals to BO over AO. Again, sinus alpha equals to BO over AO. And again, in the right triangle ABO, sinus alpha equals to BO over AO. BO equals to 5 and AO equals to 5 times root of 5. And again, BO equals to 5 and AO equals to 5 times root of 5. We have 5 in the numerator and 5 in the denominator, so 5 will get cancelled, and we left only with 1 over square root of 5. So in total, we actually found out that sinus alpha equals to 1 over square root of 5. Our test is to find out the value of angle alpha itself. In order to find out the value of angle alpha itself, we will operate the opposite function of sine, that is arc sine, on the result, and this will give us the value of alpha itself. So arc sine, that is the opposite function of sine, we will operate it on the result 1 over square root of 5, 1 over square root of 5, and this will give us the value of alpha itself. Arc sine 1 over square root of 5 is 26.565 degrees in its side. So we actually found out that angle alpha equals to 26.565 degrees. Therefore, 2 alpha equals to 2 times 26.565, that is 53.13 degrees. So this is the big angle NAB, this equals to 2 alpha, and 2 alpha equals to 53.13 degrees. We know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right triangle in BO must be equal to 180 degrees. So which angles we have in the right triangle in BO? We have alpha plus beta plus 90 degrees. In total, they must be equal to 180 degrees. So in the right triangle in BO, the sum of the angles must be equal to 180 degrees. So alpha plus beta plus 90 degrees is equal to 180 degrees. Here we subtract 90 degrees from this equation, and we found out that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. Alpha plus beta equals to 90 degrees. Here we subtracted alpha from this equation, and we found out that beta equals to 90 degrees minus alpha. So beta equals to 90 degrees minus alpha, and alpha equals to 26.565. So beta equals to 90 degrees minus alpha, and alpha equals to 26.565. 90 degrees minus 26.565 is 63.345 degrees. So in total, we found out that angle beta equals, this is angle beta, this equals to 63.435 degrees. Therefore, 2 beta equals to 2 times 63.345, that is 126.87 degrees. So this is angle BOM, angle BOM equals to 2 beta, and 2 beta equals to 126.87 degrees in its size. So in the next step, we join points M and B together by straight line. Our task is to find out the area of this green shape. By joining points M and B, we divided the green shape into 2 parts. The first part is segment MUB, this is the upper segment MUB, and the second part is the lower segment MLB. So in the next step, we calculate the area of each segment separately, and then relate the 2 segments with each other, and this will be the area of the green shape. So in order to find out the area of the upper segment MUB, I'll copy it sector ABM. In a new page, we analyze this sector ABM. So okay, this is sector ABM that are going from the original domain. 2 alpha, this is the beginning get 2 alpha. We already found out that 2 alpha equals to 53.13 degrees. AB equals to 10, AM also equals to 10. The above the area of the quarter circle, that is equals to 10. And first of all, what is a sector? A sector is a portion of a circle enclosed by 2 radii and the arc between them, arc BM. Look it again. The green shape AOB is sector AOB. A sector AOB is a portion of this circle with 2 radii and arc AB between the 2 radii. And the area of this sector AOB, the 2 radii are defined as the legs of the sector. And the area of this sector equals to the area of the circle that contains the sector, that is pi r squared. R is the radius of the circle, times the angle between the legs of the sector, that is theta, over 360 degrees. So the area of this sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector theta, over 360 degrees. So we use the new formula in order to find out the area of this sector ABM. The rounded sign above ABM is a sign of a sector. It means the area of sector ABM. According to the formula that I presented to you 1 minute ago, the area of this sector ABM will be equal to pi r squared. That is the area of the circle that contains the sector. Actually, the quarter circle, we have the quarter circle, and the radius of the quarter circle is 10. So it is pi r squared, and r is 10. So pi r squared is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 53.13 over 360 degrees. R is 10, therefore r squared is 10 squared, that is 100. So pi r squared is 100 pi times 53.13 degrees over 360 degrees. In total, the value of this expression, 100 pi times 53.13 over 360 degrees, is 46.3646 square units in size. So in total, we found out that the area of this sector A and B equals to 46.3646 square units in size. Our task is to find out the area of the lower sector MLB. This is the area of the, we have to find out the area of this lower green sector MLB or BML. From the drawing, it is very easy to see that the area of the lower sector BLM equals to the area of the lower segment BLM. This lower green segment BLM equals to the area of sector ABM minus the area of target ABM. Again, the green segment BLM equals to the area of the big sector ABM minus the area of target ABM. So we already found out that the area of sector ABM equals to 36.3646 square units in size minus the area of this triangle ABM. I've actually presented to you a new formula in order to find out the area of any triangle. This is a triangle ABC that could be any triangle. In triangle ABC, side AB equals to A unit in its length, side AC equals to B unit in its length, and the angle between side AB and side AC is theta. So the area of this triangle ABC that could be any triangle equals to A times B, that is the multiplication of the two sides by each other, times sinus the angle between the two sides, that is theta over 2. So in total, the area of this triangle ABC that could be any triangle equals to A times B times sinus theta over 2. We use the new formula in order to find out the area of this triangle ABM. According to the new formula, the area of this triangle ABM will be equal to AM times AB times sinus 53.13 degrees over 2. But again, the area of this triangle ABM, according to the formula that I presented to you, it will be equal to AM times AB times sinus 53.13 degrees divided by 2. Again, it is AB times AM times sinus 53.13 divided by 2. AB is 5, AM is 5, so 5 times 5 is 25. and AB is 10, AM is 10, so 10 times 10 is 100, and sinus 53.13 is 0.8 divided by 2. 100 over 2 is 50, and 50 times 0.8 is 40. So in total, you should know that the area of this triangle ABM is equal to 40 square units in its size. So the area of the lower segment BLM equals to the area of sector ABM, that is 46.3646 square units in size, minus the area of this triangle ABM, that is 40 square units in size. 46.3646 minus 40 is 6.3646 square units in size. So if you found out that the area of this lower segment BLM equals to 6.3646 square units in its size. In the next step, we found out that the area of the lower segment BLM equals to 6.346 square units in its size. So in the next step, we will find out the area of the upper segment BUM. This is the upper segment BUM. In order to find out the area of the upper segment BUM, I copied sector OBM in a new page and analyze this sector. This is a sector OBM that according to the original drawing, the angle between the legs of the sector is 2 beta, that is 126.87 degrees in its size. OB equals to OM, the above the radius of the semicircle, that is 5. And according to the formula that I presented to you, the area of sector OMB equals to pi r squared, that is the area of the circle that contains the sector. R is 5, so pi r squared is pi times 5 squared, that is 25 pi, times the angle between the legs of the sector, that is 126.87 divided by 360 degrees. So pi r squared is 25 pi times 126.87 degrees over 360 degrees. In total, the value of this expression, 25 pi times 126.87 over 360 degrees, in total it is equal to 27.678 square units in size. So in total, we found out that the area of this sector BOM equals to 27.678 square units in size. Our task is to find out the area of the upper segment BUM. So what is the upper segment BUM? From the drawing, it is very easy to see that the area of the upper segment, the upper green segment BUM equals to the area of sector OBM. We already found out that the area of sector OBM equals to 27.678 square units in size minus the area of target OBM. But again, the area of the upper segment BUM equals to the area of the sector BOM minus the area of target BOM. Okay. It is very easy to see that if you remove the triangle from the sector, we're left only with segment BUM. Therefore, the area of sector BUM minus the area of target BUM will be equal to the area of segment BUM. So we have to find out the area of this triangle BOM. According to the formula that I presented to you a couple of minutes ago, the area of this triangle BOM will be equal to BO times OM times the angle times sinus the angle between the two sides, that is sinus 186.87 degrees. So in total, the area of this triangle BOM equals to BO times OM times sinus 126.87 degrees over 2. BO is 5, OM is 5, so 5 times 5 is 25. And we have to divide it by 2. And sinus 186.87 is 0.8. So in total, the area of this triangle BOM equals to 25 over 2, this is 12.5 times 0.8. 12.5 times 0.8 is a 10. So in total, we should find out that the area of this triangle BOM equals to 10 square units in size. So in total, the area of this upper segment BOM equals to the area of sector BOM, that is 27.678, minus the area of this triangle BOM, that is 10. 27.678 minus 10 is 17.678 square units in size. So in total, we found out that the area of this upper segment BUM equals to 17.678 square units in size. Our task is to find out the area of this green shape that consists of the area of the upper segment BOM plus the area of the lower segment BLM. We already found out that the area of the upper segment BOM equals to 17.678 square units in size plus the area of the lower segment BLM that equals to 6.346 square units in size. So the area of the green shape equals to the area of the upper segment BOM that equals to 17.678 square units in size plus the area of the lower segment BLM that equals to 6.346 square units in size. So 17.678, that is the area of the upper segment BOM plus the area of the lower segment BOM, that is 6.346 square units in size. In total 17.678 plus 6.346, in total it is equal to 24.0426 square units in size. So in total we actually found out that the area that we are looking for this question, that is the area of this green shape, equals to 24.0426 square units in size. Okay, thank you very much.